So hello everyone, this is week 5 and we start with another new chapter in this week, which is chapter 4, and in this chapter we are going to cover the third layer, the third layer from the top of the TCP/IP model. The topmost layer is application layer, then transport layer, and it is actually, we can call it as the middle layer, the network layer. Network layer is a huge layer and it has a lot of functions to do. So starting from this week until week 7 and even after the midterm exam, we are going to continue with the network layer because it's a huge layer. It has many functions, many responsibilities and many functions to perform. This layer is a combination of both hardware and software. The topmost two layers, application and transport, they are purely software based layers. Network layer is a combination of both hardware and software, and the bottommost two layers, which is the data link layer and the physical layer, they are the purely hardware layers. So let's start with the network layer. In this chapter, first of all, I will discuss what are we going to discuss in this chapter, and today, in this week, in this class, what I am going to cover. So these are all the things that we are going to cover in chapter 4. It's not like we are going to cover all these things in 1 or 2 weeks. We will be covering few things before the midterm, and we will be covering few things after the midterm. So in this week lecture, I am going to cover 4.1 which is introduction, 4.2 virtual circuit in datagram, 4.3 which is what's inside a router, and in 4.4 I am only going to cover until the datagram format. So in 4.4, the IPv4 addressing, ICMP and IPv6, it will be covered in the next week. So this is all until from introduction to datagram format will be covered this week. Alright, so let's start with this. We know that the network layer is the middle layer of the TCP/IP model. It is responsible for transporting the segment from the sending host to the receiving host. So it works from host to host, whereas our transport layer works from process to process. It works, transport layer works between the processes, whereas network layer works between the host. Now if you transports the segment from sending to the receiving host. Now on the sender side, it encapsulates the segments which it receives from the network layer and forms a datagram. So it encapsulates the segments received from the network from the transport layer and forms a datagram. And on the receiver side over here, it decapsulates the segment from the datagram and delivers the segments to the transport layer. So on receiving side, it decapsulates the segment from the datagram and then delivers those segments to the transport layer. Network layer protocol is everywhere in host and the router. So if you see over here, our intermediate devices, the network core, which we call it as the network core. Network core works only on 3 layers. The upper 2 layers, transport and the application layer, are not present in the network because simply transport and application layer, they consist of the applications which are used by the end user. So if you see over here, our network core only contains the bottom 3 layers, which is physical layer, data link layer and the network layer. Now what does the router does in the network layer? Router examines the header fields in all the IP datagrams that it receives and which pass through it. So by examining the header, it decides which output port a particular datagram should be directed to so that it can reach to its destination. Alright, so if you see over here the animation, so it goes and then it is delivered over here. This is how it works. I show you again. So for example, You make a message, it goes to network layer, then it goes to all these links, and then from the network layer to the application layer. Alright, moving ahead. Two important network layer functions are forwarding and routing. Although we discussed about it, I think in chapter 1. Forwarding is moving the packets from the router's input port to the appropriate router port, and routing is to determine the path, the shortest path or the perfect path between the source and destination, so that that path can be taken by the packets. Now for routing we use certain routing algorithms, which we will be talking about later in this chapter. So forwarding is routing is like it's a process of planning a trip from place A to place B. For example, you come to the college, so you plan a trip, you plan a path, you take a path from your home to the college. So that is called as routing. Now, while you plan your trip, there may be certain areas you have to pass through. For example, you may have to pass through Khalij, you may have to pass through Jalmuda, or you may have to pass through certain other district. So passing through those districts, that is called as forwarding. That means you enter to a district, you leave that district. That is called as forwarding. So process of getting through single interchange, that is called as forwarding. So routing is the complete path or the process of complete trip from source to the destination. For routing, of course, we use the routing algorithms. We are going to talk about it later in the slides. So how does the router decides about the forwarding? So routing algorithm actually determines the end-to-end path through the network, and forwarding table, this is the forwarding table, it determines the local forwarding at the router. So the basic purpose of the forwarding table is to determine the output port to which the packet should be directed to. So for example, let's assume that this packet arrives at this router at a particular point. So when this packet arrives at the router, what this router will do, it will examine the header, and when it examines the header, it finds this number 0111. Now when it finds this number, it consults its forwarding table. So in local forwarding table, it says that if the header value is 0111, the packet needs to be directed to the output link number 2. So the heading local forwarding table tells this router that this packet has to be forwarded to the link number 2. So when the packet arrives, it will first of all remain in a queue if there are other packets, but if there is no queue, this packet will be directly forwarded to the link 2. So when this packet arrives at, let's assume that this router, again it will check its forwarding table, and so on. The packet will be this way, packet will reach to its destination. If you see, each of the router has the forwarding table built over here. So how this routing table or how this forwarding table is built, what is the algorithm or what is the process used, we will talk about it later. Alright, so important point, third important function is connection setup. So third important function in some important architecture, before datagrams flow to end host connecting with the routers, they must establish the virtual connection or the logical connection. But it is not always the case. If we are using the virtual datagram, then only the virtual connection is established. If we are using a datagram, a virtual circuit network is used, then virtual connection is established. If we are using a datagram, then no virtual connection is established. Your internet follows the datagram connection. So while setting up the virtual connection, routers are involved, and it defines actually the certain path. What is the difference? How do we differentiate between network versus transport layer in terms of the connection service? Network layer works between two hosts. So for example, we have a PC here, we have a smartphone here. So it works between two hosts, whereas transport layer works between two processes. So for example, let's assume that on a PC mail is working and over here also mail is working. So transport layer will work between two processes. Alright, so next is, what are the services provided by the network layer in transporting or in sending the datagrams from sender to the receiver? So what are the services a network layer is providing? The first service that the network layer provides is the guaranteed delivery. Guaranteed delivery is a service which makes sure that the packet will definitely arrive at the destination. So this makes sure that it guarantees that the packet will definitely arrive at the destination. Second is guaranteed delivery with bounded delay. There can be some delay, but packet will arrive. So this service not only it ensures that packet will arrive, but it will arrive within a specified certain host to host delay bound. For example, it can be 1 millisecond, it can be 100 milliseconds. So some delay bound is specified for the packet. There are other services also which are provided to flow of packets between the source and the destination, which is in order packet delivery. So this service of the network layer, it guarantees that packets arrive at the destination in the order that they were sent. So for example, source sends 5 packets, 1, 2, 3, 4 and 5. So this service ensures that the packet will arrive in the order of 1, 2, 3, 4 and 5 and not as 3, 5, 2, 4 and 1. Next is guaranteed minimal bandwidth. So this service of the network layer, it emulates the behavior of the transmission link of a specified bit rate between the two hosts, between the sender and the receiver. So it makes sure that the minimal bandwidth, whatever is the minimal bandwidth provided by the transmission link, is always provided between the sender and the receiver. So as long as the sender host transmits bits rate below the specified bit rate, no packet is lost. And when each packet arrives with a specified, for example, whatever the bit rate is specified, it arrives within a pre-specified host-to-host delay within the 40 milliseconds. So it guarantees the minimal bandwidth. Next is maximum jitter. So basically, what is a jitter? Jitter is the delay in the subsequent delay in the arrival time of the subsequent packets. Many times you might have noticed or you might have experienced while you are downloading a video or you are watching a video, it plays for a while, then it stops and the cursor just revolves, and then after a while it plays again. So that is called as jitter. So maximum jitter, it guarantees that amount of time between the transmission of two successive packets, two subsequent packets at the sender is equal to amount of time between their receipt at the destination. This means that at the sender, if the first packet is transmitted at 0 millisecond and the second packet is transmitted at 5 milliseconds, so the time difference between the first and second is 5 milliseconds. For example, let's say 1. So 4 milliseconds. Now this time difference will be same at the destination. So at the destination, it will arrive at time is equals to 1 or whatever the time, packet 1 will arrive at 1 milliseconds and packet 2 will arrive at 5 milliseconds. This is what is called as jitter. Jitter means the time difference between the two subsequent packets at the sender side is equal to the amount of time between at the destination. Next is network layer offers security services also. So using a secret session key known only by the source and destination host, network layer at the sender side can encrypt the payload of the datagrams which are sent to the destination host. Network layer in the destination host, it will be responsible at the receiving side, it will be responsible for decrypting the payloads. So with such a service, some sort of security, confidentiality can be provided to all the transport layer segments between the source and destination. And also confidentiality, in addition to the confidentiality, it can also provide data integrity and the source authentication services. So this was only a few services that a network layer can provide. Although there are many other variations possible, network layer can provide much more services than what we have discussed now. Let's move on to the next topic, which is what's inside a router. Alright, so let's discuss over here the components of a router. The components of a router. What are the components of the router? There are four main components of the router, which are input port, output port, switching fabric, and a routing processor. So what are these components, and how do these components interact with each other? Let's talk about this going ahead. So as we know, the two main important functions performed by router are routing and forwarding. So routing is providing a path between source and destination for all the packets, and forwarding is transmitting the packet from the router's input to the router's output port. So forwarding the datagram from incoming to the outgoing link. So if you see over here, we have this is the switching fabric at the center, then there is a routing processor, and then there are input ports and the output ports. So this is how the internal structure or the internal architecture of the router looks like. Let's understand the function of each part in detail. Alright, so forwarding tables, they are pushed to the input ports, and this is the forwarding data plane, right? So let's first of all talk about input port. Now input port, it performs many functions. It performs the physical layer function. It performs the physical layer function of terminating an incoming physical link to a router. It can perform the data link layer function also, which is needed to interoperate with the data link layer. It also performs the lookup and the forwarding function. Alright, so let me first of all discuss one by one. It performs the physical layer function. Okay, if I go back to the diagram, physical layer function, do you see over here we have in the input layer we have different boxes colored and their different sizes. So it performs the physical layer function. So if you see the leftmost box, this one, the small green box on the input port, and the rightmost box on the output port. So it performs the function of the physical layer function. It also performs the data link layer function, which is represented by the middle box in the input and the output port. And it also performs the lookup and the forwarding function. So it is represented by rightmost port in the input port and the leftmost box in the output port, which is the red color box. Basically it performs the lookup and forwarding function so that the packet can be forwarded into the switching fabric. So packet can be forwarded to the switching fabric of the router and it emerges at the appropriate output port. Then control packets, for example, packets which carry the routing protocol information, they are also forwarded from input port to the routing processor. So in practice, multiple ports, they often gather together on a single line card within a router. So if you see, input port performs many functions related to the physical, related to the data link layer, and related to the forwarding and the lookup function. Next we talk about switching fabric. So let's talk about routing processor first, as given over here. Routing processor, as we know that processor is always the main part. So routing processor is running the routing algorithm, which is implemented as a software to produce the forwarding table, and this part is called as routing or the management control plan. So it is executing the routing protocol, it maintains the routing information, forwarding table, performs network management functions within the router. So processor is again the heart of the routing processor. A copy of the forwarding table is distributed to the input port, which is also done by the routing processor. Forwarding table. So forwarding table is nothing but a routing table. It is used to specify the path or the output port for each incoming packet based on the header of the packet. Input port functions, so this is what I told you. It performs the physical layer function, which is equal to the bit level reception. The middle layer performs the data link layer function, for example Ethernet, receiving the protocol, and the last performs the looking, forwarding, and the queuing function. So it's a decentralized switch. So if the datagram destination is given, it will look up the output port using the forwarding table in the input port memory, and if datagram arrive faster than the forwarding rate, it has to queue the datagrams into the memory of the router. Okay. Now let's talk about switching fabric. Now what is a switching fabric? Switching fabric actually connects the router's input ports to the output ports. If you have seen in the diagram also, so this high-speed switching fabric, it connects the router's input port to the output port. This switching fabric is completely contained within a router, a network inside of a network router. So there is a network inside of a network router. So basic function is to transfer the packets from input port to the appropriate output port. Switching rate, it's the rate at which packets can be transferred from input to the output port. Now there can be three kinds of switching fabric. It can be a switching via memory, it can be a switching via bus, it can be a switching via crossbar. Now let's understand what's the difference between them: switching via memory, switching via bus, and switching via crossbar. So switching via memory, they were the first generation routers. The simplest and the earliest routers were often traditional computers with switching between input and the output port, which was done under the direct control of the CPU. So the traditional computers with switching under direct controller of CPU. Now in this, input and the output ports, they functioned like a traditional input-output device, and the input port with an arriving packet is first signaled the routing processor via interrupt. So what happens is, when the packet arrives, packet is first of all copied to the system's memory, which is the memory. Then CPU extracts the destination address from the packet's header, looks up the output port into the forwarding table, and then copies to the output port. Then copies that datagram to the output port. So if you see over here, when it arrives, it is stored into the memory. First of all, packet is copied to the system memory. Now CPU will extract the destination address from the packet's header. It will look for the output port and then it will copy it to the output port. If you see over here, like this. But the basic drawback is speed is limited by the memory. So if it's a high speed memory, speed will be faster. If it's low speed memory, speed will be slower. And another is only one packet can be transmitted at a time. So that was another disadvantage. Alright, so coming to the next, which is switching via bus. So what happens in this, let's understand. Okay, so in this switching technique, input port transfers the packet directly to the output port over a shared bus. So if you see over here, this is the input port, this is the output port, and both of them, they are connected through a shared bus. So input port, they transfer the packet directly to the output port over a shared bus, and there is no intervention of the routing processor. Although the routing processor is not involved in the bus transfer because the bus is shared, but only one packet at a time can be transferred over the bus. So only one packet can travel on this bus. A packet arriving at the input port and finding the bus busy with the transfer of another packet is blocked from passing through the switching fabric, and it is queued at the input port. Suppose packet 1 arrives. It sees that there is another packet which is being transmitted on the bus. So this packet will not be transmitted unless and until the packet before it is transmitted fully to the output port, and in this scenario the packet which has arrived now will have to wait. It will be queued up. Because every packet must cross the single bus, switching bandwidth of the router is limited to the bus speed. So again, switching is limited by the bus bandwidth, and that is one packet at a time can cross the bus. The last technique is switching via crossbars. So we also call it as switching via interconnection network. So this is actually a way to overcome the bandwidth limitation of a single shared bus. So the basic idea is to use a more sophisticated and advanced interconnection network, similar to those that have been used past to interconnect the processor in a multiprocessor system. So what is a crossbar switch? If you see over here, this is a crossbar switch. This is a crossbar switch. A crossbar switch, it's an interconnection network consisting of two N buses and that connect N ports to N input ports to N output ports. So in this case, number of input ports is same to the number of output ports, but the number of buses are 2 times N. 2 times N. What does 2 times N means? If there are N input ports and N output ports, number of input ports should always be equal to number of output ports. Then the number of crossbars, or we call it as number of buses, should be 2N. For example, over here, number of input ports is 3, number of output ports is 3. So what is my N? N is 3. So in this case, the total number of interconnections, or we call it as total number of bus, should be 2 multiplied by 3, which is 6. Let's calculate number of buses. Let's check number of buses. If you see, this is the first bus, second bus, third bus, fourth bus, fifth bus, sixth bus, right? And total number of interconnection point should be n square. If you see interconnection point 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is n square. So number of interconnection points is n square and number of buses is always 2 multiplied by n. So what is the general idea behind it? The general idea is when a packet arrives at the input port, it travels along the horizontal bus, which is, if you see, horizontal bus attached to the input port until it intersects with the vertical bus leading to the desired output port. So if for example packet 1 arrives and it wants to go to X, it will travel on this horizontal bus and until it finds the intersection for the desired output. So this is the intersection or intersection with the vertical bus which leads to the desired output port. If the vertical bus leading to the output port is free, now if this bus is free, then the packet is transferred to the output port. But if the vertical bus is being used by someone else to transfer the packet from another input port to the same output port, then the arriving packet is blocked and it must be queued in the input port. So let's check with this example which is given over here. So for example, when a packet from port A, this is input port A, needs to be forwarded to port Y, so it must travel on this horizontal bus, right? This horizontal bus. When it arrives at this intersection, it needs controller closes the cross point at the intersection of the two buses and it is transmitted. But the problem is, if two sources, let's say A and B, they want to send the destination, the packet to the same destination. Now in this case, one of them should wait, either A or B. So if B is sending the first and the packet at A arrives, the packet must be queued over here at the input port. After B finishes sending the data, the packet to the output port Y, then only input port A can send its packet. So this is one of the disadvantage. Last thing is output port. So output port, let's discuss about it. So what does the output port does? Output port stores the packet that have been forwarded to it through the switching fabric and then transmits the packet on the outgoing link. The output port performs the reverse functions of the input port, or it performs the reverse function of the data link physical layer functions at the input port. But when the link is bidirectional, an output port to the link will typically be paired with the input port for that link. So if you see, it buffers, it queues, then it sends, then it terminates. So buffering is required when datagrams arrive from the fabric faster than the transmission rate. That's why the buffering is required. So in the input port, queuing delay and loss may occur due to the input buffer overflow, and in the output port, queuing delay and loss may occur due to the output buffer overflow. So in both the points, delay may occur. Alright, the last topic of this week's lecture that we are going to talk is IP protocol, Internet Protocol. Quite a huge topic. We are not going to finish it in a single day or a single lecture. Rather, we are just going to talk about datagram format in this. Let's understand first of all the IP layer components. Okay, so the IP protocol we are going to discuss in this section. Routing protocols. Routing protocols determine the path a datagram follows from source to the destination and help in finalizing or selecting the path of the datagram. Then ICMP, Internet Control Messaging Protocol. It's a protocol, a facility to report the errors in the datagrams and respond to a request for certain network layer information. This week you learned about ping command. So ping command belongs to the ICMP protocol. The protocol related to the ping command is ICMP. So the basic purpose of the ICMP is to report the errors and to respond to the request for the network layer information. Alright, so if you see over here, the network layer is a huge layer and it lies between the transport layer and the data link layer. There are many protocols, routing protocols for the path selection. We are going to talk about this. IP protocol for it does addressing. It is related to addressing datagram format, packet handling conventions. Then we have ICMP protocol. It is related to error reporting, router signaling. Routing protocols also help in making the forwarding table. So a very huge layer and many functions. Alright, so let's first of all talk about IP datagram format, just like we talked about TCP segment we talked about. So the size of IP datagram format is 32 bits. We know that the size of our IP address is 32 bits, which makes it 4 bytes. Now what are the various fields in those 32 bits or in those 4 bytes? If you see, the first one is the version. Version tells us the version of the IPv4 and the version uses 4 bits. So 4 bits are used by the version, for example IPv4 or IPv6. Then is the header length. So the header length, because IPv4 can contain variable number of options, so again header length is 4 bits. These 4 bits are needed to determine where in the IP datagram the data actually begins. So header length tells us the number of bytes of data which this IP header is, which this IP datagram is carrying. Then is type of service. Type of service is used to determine the type of data it is carrying. For example, it might be useful to distinguish between real-time datagrams or those used by IP telephony from non-real-time datagrams, for example FTP. So what is the type of data? Length tells us the total length of the datagram including the header length, right? So header length and length. Header length tells us the length of the header, whereas length tells us the total bytes of the total size of the datagram. So this is the total length of the IP datagram. It tells us header size plus data measured in bytes. So this field is 16 bits long, which is 2 bytes. So the theoretical maximum size of the IP datagram is maximum is 65,535. However, datagrams are rarely larger than 1500 bytes when they are being transferred, but the maximum size of datagram it can have is 65,535. Alright, so now we have 16-bit identifier, we have flags and fragmentation. These 3 fields, they have to do with what we call it as IP fragmentation. In the next slide I am going to discuss it, and the new version of IPv6 does not allow fragmentation. So all these are used for the IP fragmentation. Time to live, TTL field. Next is TTL field. You might have seen the TTL field in the ping command, right? When you use the ping command, there was some TTL is equals to 128. So what does this TTL means? TTL field is included to ensure that datagrams are not in the network forever. So remember we talked about round trip time in the transport layer. So this is similar to that. So this field is decremented by 1 each time datagram is processed by a router. So if the TTL field reaches 0, the datagram must be dropped. So before the TTL reaches 0, the datagram should reach to its destination. So when the TTL field reaches 0 and the datagram is still in the loop or in the router, it will be dropped by the router. In that case, the sender will have to send the packet again. Alright, so upper layer protocol. This is upper layer. So this field specifies what is the protocol used by the upper layer. It can have either TCP or a UDP. So this specifies the protocol used by the upper layer. Next is the header checksum. Header checksum is used to calculate the errors, detecting the bit errors in the received IP datagrams. So this field is basically for the error detection. Alright, next is 32-bit of source IP address and 32-bit of destination IP address, which you all are familiar, IP address of the source and IP address of the data. Next is options, which can be like timestamp, record route taken, list of routers visited. So these are the various options. Last one is data. Data is the actual user data which the user is sending. It is of variable length, or it can be typically a TCP or a UDP segment. Right? So how much overhead? So how much overhead the IP datagram carries? IP datagram has, the header size of the IP datagram is 20 bytes, right? This all is 20 bytes, right? So IP header, the size of IP header is 20 bytes, and we learned in the TCP, when we were doing the TCP, the size of the TCP segment is 20 bytes, right? 20 plus 20 makes 40. This is a fixed that it will have, because header, IP header will be 20 bytes, TCP header will be 20 bytes, plus this size option will be variable, which is the users related to the user data or whatever the data user is sending. So TCP segment is 20 bytes, 20 bytes of IP header plus 20 bytes of TCP header along with the application layer message. So this is variable size, and all of this cannot be greater than 65,535. This is the maximum size of IP header. But in practice, normally the datagrams are not larger than 1500 bytes, because if we have too big datagrams, then routers will take a lot of time to process those big datagrams. So normally the maximum size is the maximum size of the datagram is 1500. So 1500 means this is 20 plus 20, 40. 1500 minus 40. If the size of, for example, the length of the IP datagram, if I find out, for example, the length of the IP datagram is 1000 bytes. Here in this field, in the length, if it is written 1000 bytes, I want to find out how much is actual data. So actual data is 1000 minus 40. Why minus 40? Because out of 1000, 20 is for the IP header and 20 is for the TCP header. So 1000 minus 40 means about 960 bytes is the user data, right? So this is how we calculate. Alright, now we talk about fragmentation and reassembly. Fragmentation actually means breaking something, and reassembly means joining back. So network links have MTU. MTU means maximum transmission unit, the maximum amount of data that can be carried by data link frame. Different link types, for example, a router will, a copper cable will have different MTU, fiber optic will have different MTU. So different link types, they have different MTUs. Large IP datagram. So if a device is sending a large IP datagram, it has to be fragmented in the network layer. Fragmentation means if the datagram is large, it will be broken down into certain pieces. So one datagram may become several datagrams. So this is at the sender side. But when it arrives at certain point at certain link whose maximum transmission unit is greater, then these several datagrams can be recombined back. This is called as reassembly. So fragmentation means we are giving one large datagram, but when it comes out of a link, for example a router, it is 3 smaller datagrams, because the maximum transmission unit of that router or a switch may be lesser. So this is called as fragmentation of the datagram. And why we need fragmentation? Because the maximum transmission unit of different links are different. So the link may not be capable of sending a large datagram. That's why it fragments the large datagram into multiple smaller datagrams. Alright. Datagrams fragment can be reassembled only at the final destination, not inside the router. So if the datagram is fragmented by certain link, reassembly is only done at the destination network layer, not inside the router. So inside the router, the reassembly cannot be done. So for example, in the previous slide, this datagram was divided or fragmented into small 3 datagrams. Now these 3 datagrams will be combined into as a single datagram only when they arrive at the destination. Now how it will be combined? IP header bits are used to identify the order related to the fragments and the first and the last fragment of a single datagram. So there are certain bits in the header which are used to identify the fragmentation bits. For example, if I go to the IP header over here, we have over here fragmentation offset, flags and 16-bit identifier. So these 3 fields are used for fragmentation and assembly. Alright, coming back. Okay, so we have an example over here showing fragmentation and reassembly. Okay, so let's understand this IP fragmentation and reassembly. Let's assume that a datagram, the size of the datagram is 4000 bytes arrives at a link, but the maximum transmission capacity of that link is 1500 bytes. So that means this complete datagram cannot be transmitted from that link as a single datagram. So it has to be broken down. Now how many fragments should be made out of this? So because the maximum transmission capacity is MTU is 1500, so 4000 divided by 1500, which makes 2.66, which is equal to 3 fragments. So that means 3 fragments should be made. Now note that out of 400 bytes, we just now discussed that size of IP header is 20 bytes, right? So out of 400 bytes, it is only 3980 bytes which contain the user data. Rest 20 bytes is the IP header. So the user data is 3980 bytes. So it arrives at a router and it must be forwarded from a link with MTU of 1500 bytes. So that means this has to be broken down, right? So one large datagram now will become the 3 smaller datagrams. So how it will become the 3 smaller datagrams? The first length, of course, we will first of all how it will be broken down. So first length will be equal to the first length of the first datagram will have the maximum length of the equal to the MTU capacity of the link, which is 1500. 1500 means the user data is 1480. I am not going to talk about 1500. It will be 1480. Right? Identification can be anything. fragmentation flag is set to 1. That means there is one more fragment of this IP datagram. Offset is 0. Offset means data is inserted from the beginning of byte 0. That means beginning of 0 the data has been inserted. So first 1480 bytes of the data have been inserted. Now let's come, because there is another datagram. So next 1480 bytes are inserted over here. Alright. So offset 1, fragmentation flag 1 means that there is one more fragment. Offset 185 means that data should be inserted at the byte 1480. It should be inserted beginning at a byte 1480. So out of 3980, 1480 are done. Now from beginning of 1480, the second datagram should start. This is the meaning of the offset. So how this offset is calculated? Each byte has 8 bits. When you multiply 185 with 8, you get 1480, or you divide 1480 by 8, you get the 185. So this is how the offset is calculated. So next we still have one more datagram because the fragmentation flag is set to 1. Now how this will be calculated? So 1480 have already been done. So what was the total size? 3980. Out of 3980, 1480 and 1480 has already been sent through separate two datagrams. So how much is left? 3980 minus 1480 minus 1480, which will roughly come to which is 1480, which is 2960, right? 2960. So 2960 means we are just left with 1020 bytes with the IP header, which is 1040 bytes. So next IP datagram will carry only 1020 bytes. Identifier we are not concerned. Fragmentation flag here 0 means that there is no more fragment. Offset 370. How is offset 370 calculated? Divide this 2960, because 1480 plus 1480 is 2960. Divide it by 8. Whatever the number you get, 370, that will be offset. Or what you can do, 370 multiplied by 8, you get 2960. So that will be the offset. So offset is nothing but the quotient. Alright, so offset is nothing but the quotient. So offset basically specifies 370. It specifies that the data should be inserted beginning at a byte 2960. That's why the offset is 370, because 1480 plus 1480, this data has already been sent, which is 2960. When you divide this 2960 by 8, why by 8? Because each byte is 8 bits. So when you divide it by 8, you get the quotient 370. So this is what we get as offset. So this is how the fragmentation is done, and at the at the receiver point, when it arrives, when these three datagrams arrive at the receiver, they will be reassembled at the receiver and not in between at any router. So this is how the fragmentation, IP fragmentation is done. Fragmentation flag 0, it indicates that it is the last fragment, and if fragmentation flag is set to 1, that means there is further more fragment. In the flag field, whatever the flag fields are there, they are always 1 bit, and they always take either the value 1 or 0. 0 means flag is not set, 1 means flag is set. If the flag is set, which is 1, that means there is another fragment. If the flag is not set, which is 0, that means there is no other fragment. Alright, so we finish our this week's chapter number 4's topic over here. In the next next class, we are going to discuss about IPv4 addressing, ICMP and IPv6. Although IPv4 addressing, many of the things you have already learned in lab, but still we will be doing it in a little more detail. And thank you so much.